Hello, everyone, and thanks for joining us today. My name is Jules Lancet of the Space Medicine and Life Sciences Project Group inside the Space Generation Advisory Council, and we are very excited for today's first session of the new Health in Space series, How to Deal with a Medical Emergency in Deep Space. So why deep space? In recent years, we've seen plans being made to go back to the moon and even further to Mars. Humankind has never traveled out this far or went on such long duration missions. And the technology to make such missions possible is very important in terms of launch systems and spacecraft. But how will we deal with the health and medical needs of astronauts when venturing out in deep space? The human element in this story requires a delicate balance in its outer environment and its organs, its own internal systems. And the risks introduced with these next generation human spaceflight missions is what we'll talk about today. And then more specifically, what if the balance is off in an acute way? How do we deal with appendicitis in space or a broken leg on Mars? I hope to find out today, and I probably will, considering the two pioneer thinkers on this topic that we have invited to speak. So let me introduce to you both of their backgrounds first. First, we'll hear from Chris Leonhardt. Chris is the element scientist for exploration medical capability at the NASA Human Research Program. He was trained as a medical doctor, served as a flight surgeon for simulated missions to Mars, and is now leading a team investigating what is needed on the actual manned missions to Mars. He also is faculty member at the International Space University and at Baylor College of Medicine. And after Chris, we will hear from Anthony Yuan, who is an emergency physician and professor of emergency medicine at Weill Cornell Medicine in New York. And he is also one of the founders of the project group Space Medicine and Life Science, as the latest addition to the Space Generation Advisory Council last year, after having already served the council as its treasurer. And before pursuing a medical career, Anthony received a degree in mechanical and space engineering, so I'm sure you will also conclude that he's too more than qualified to tell us about emergency medicine in space. And we'll get you to both speakers shortly, but first, a few housekeeping items. You have been muted on entry to avoid background noise and disruptions. The session will be recorded for later viewing. And this webinar, as it is a feat of engineering, is not comparable to anything being accomplished in space, of course. However, this is still a global effort with your speakers and moderator being in 3 different time zones already, not counting you, the audience. Of course, we are not counting on any disruptions, but Murphy's Law does apply. So in that case, please bear with us as we try to restore the live session as quickly as possible. And finally, please hold off on Q&A until the end. However, do feel free to use the chat box during the presentation for questions and comments. That being said, I'd like to encourage attendees to unmute themselves during the Q&A and ask their questions aloud rather than use the chat feature. Now, I have been talking a lot. Let's get to our speakers. Hi, Chris. Thanks for being with us today from Houston, I think. I'll be switching over to you now. If you don't mind to share your screen, I'll hand you the virtual floor. Chris, we have discussed this topic of today already back in 2017, I think. Of course, you have been working on this for a longer time. I'm very much looking forward to your latest insights in this field. The virtual floor is yours.
Thank you very much, Jules. I really appreciate the invitation from you and Anthony to be here. And good morning, everyone from rainy Houston, where there's a tropical storm or tropical depression on top of us right now, but the flooding's not too bad. So we're in good shape here. Jules, can you confirm that you can see my screen?
Yes, we do. We do see your screen. Thank you.
Excellent. So I'll get started. So I appreciate the introduction. For those of you who are unfamiliar with the Human Research Program at NASA, our job is to look at all of the health risks and hazards to humans in space flight for exploration missions. So that includes to the moon, to the lunar orbit, lunar surface, as well as to Mars. And our primary focus is looking at the long game. So we typically focus most of our efforts on what humans will need to maintain their health and performance for missions to Mars. And the group that I work for at the Human Research Program is called Exploration Medical Capability. And our job is to advance medical system design and risk-informed decision-making so that we can improve and preserve the human health and performance of astronauts in space flight for exploration missions. In order to establish my credentials for today, I figured I would just show some of my space nerd photographs, if you will. The one on the top left is me sitting in the commander's seat of the Space Shuttle Discovery while it was being refurbished in between flights. On the top right is me with the Canada arm from one of the space shuttles that was in between flights as well. Bottom left are the tanks that sit near the launch pad, or used to sit near the launch pad at the Kennedy Space Center during shuttle missions. And those were the tanks the astronauts would use to escape the site if there was a catastrophe on the pad. And the bottom right is an opportunity I had to view a shuttle launch, and I took that picture myself, and that is the Space Shuttle Discovery taking off. And so that's, I've been a proud space nerd for a long time, and happy to share my insights with you about medicine in space and how we're going to deal with that for exploration. So the first question, of course, has to be, do we even need medicine in space? Maybe we could just pick really healthy people and send them into space and nothing bad will happen to them. Well, we have data that says that that is not the case. So here you see a list of conditions that have occurred in spaceflight. This list is current as of 2017. And you can see here that there are a number of medical events that do occur in flight. And these events, while some of them are fairly minor in their presentation, they can become more serious over time, or these events will compound on top of each other to affect the health and performance of our crew members. So we know that medical events occur in space. We also know that astronauts are human, and humans break down over time. And so what you see here is a list of conditions that have occurred in astronauts on the ground in between missions. And so in theory, any one of these conditions that occurred on the ground could have just as easily occurred in flight to the astronauts. And so when we're considering how we develop medical systems for space exploration, we have to give consideration to these types of conditions because their possibility of occurrence is real. Now, how likely they are to occur in mission or in flight is a different case, and we'll get to that a little bit later on. So before we can talk about the future, we have to define the present. And so right now, the way that we take care of astronauts on the International Space Station is using something called the CZECHS system. The CZECHS system is a series of component systems that are made up of different support groups and technologies that are used by the astronauts to maintain their health, to do health maintenance, and to do environmental health. And this system that we have right now is not a system in the true sense of the word, because all of these components are individual components and they're not all connected together. And so you could swap out any one piece of this system and put in another piece, and it won't necessarily have a detrimental effect on the whole system. So it's not an integrated system, it's more of individual components that are put together. And we use this system in mission to take care of the crew through the use of a number of different modalities. So the first thing we do is we will provide live real-time communications and guidance to the crew on how to do these procedures in flight. So every picture you see there, there's likely someone on the ground who's giving advice to the crew member about what exactly to do next and how to follow the procedures. The other way we'll provide care in mission is just keeping an eye on things. And so we real-time live monitor, especially during significant events like spacewalks. There's a good amount of information on the space station that is captured by individual components or individual technologies. And then that information is transmitted to the ground. And so that's the store and forward capability. But what we don't really do in mission right now is autonomous medical care, meaning that the crew doesn't just take care of themselves. They have an awful lot of support from the ground and training on the ground to try and get them ready for their mission. And so one of the things that we will be looking at more in the future at NASA is how do we create a progressively Earth independent crew with respect to medical care. At the end of our missions on the International Space Station, our astronauts and the cosmonauts and all the crew members return home, and they have a huge greeting party, meaning that they are not responsible for getting out of the capsule themselves. They are not responsible for transporting themselves. And if they had any issues, there's a large team of people there ready to take care of them. That is clearly not going to be the case on Mars. And so that the paradigm that we are used to of large contingencies or large groups of ground support people is simply something that will not exist in the future, and we have to prepare for that future now. So just to give you a little context here, for the last number of years, we've been doing missions where we fly on the Soyuz to the space station, and then we have 6 months and perhaps longer crews on board the International Space Station. We're working in the short term towards having the commercial crew program, working at NASA, which is SpaceX and Boeing launching astronauts to the space station. NASA is also working on the multi-purpose crew vehicle, or the Orion vehicle, which is our deep space transport vehicle. And then the Gateway is now being developed, which is a small space station that will be in orbit around the moon. And ultimately, in order to get to Mars, we're going to have to develop a deep space transport vehicle and the capability to land humans and significant amount of resources on the surface of Mars in order to enable Mars surface missions. So the Gateway, which you see a representation of here, is the next phase in our human exploration plans when we go beyond low Earth orbit. And what you see here is the Orion vehicle coming to meet the Gateway. Ultimately then, there will be work done to develop a deep space transport system, which would likely dock at Gateway and prepare at Gateway for its missions into deep space. And then last but not least, the Mars transport vehicle would be the one doing the transit to the Mars area. And so this is the plan that NASA is looking at long term. And ultimately, it all leads to trips to Mars, which will be either orbital trips in that we will just go and orbit the planet, and then eventually there will be landing trips as well as the technology is developed. But these missions to Mars, the shortest period of time is probably, sometimes you'll hear between 6 and 9 months. It's probably realistically more between 9 and 12 months to get people to Mars and then back again. And so the missions that we're looking to do to Mars are significantly longer than anything we have ever done before in space flight, including in low Earth orbit. And so ultimately, when you think about the way that we provide medical care right now, on the International Space Station, we have real-time communications. We have the ability to evacuate people if there's any significant medical event that occurs. And we right now can have those people on the ground within 6 to 24 hours. And we have the ability to consistently do consumables resupply. So if you forgot something, you can call down to the ground and ask for it to be put on the next vehicle. If you need new medicines because you used all of them or some of them expired, you can call down to the ground and ask for more of those. When you're on your way to Mars, that is simply not going to be the case. So the communication delays will get longer and longer as you go away from the Earth, up to 20 minutes in each direction. There's even a possibility that there will be a time during a Mars mission where the sun will be between Mars and Earth. And during that period of time, you could lose communications entirely for up to 2 weeks. We clearly won't be able to turn around and come home again if someone develops a medical event that's significant, 4 months on the way to Mars. And the ability to do consumables resupply does not exist. There may be ability to pre-deploy resources to the Mars orbit or to the Mars surface, but there certainly won't be any resupply options. And those pre-deployment options are limited as well, because if one of the things you want to pre-deploy are medicines, if those medicines degrade in the space environment faster than they do on Earth, they may be no good by the time your crew arrives. So our paradigm for how we provide medical care on the space station and how we're going to provide medical care for exploration missions must change. But how do you scope for a system like this? As a person who works in the hospital in the emergency department in Houston, I have at my disposal in the hospital significant resources, lots of resupply, lots of consultants that I can talk to for various problems. I have an entire hospital essentially at my disposal. You cannot take that kind of mass and volume on a mission to Mars. And so ultimately what we have to be able to do is we have to be able to scope a medical system appropriately to the mission. And so one of the ways that NASA has tried to confine or constrain that problem is to define the conditions that are most likely to occur during an exploration mission. And so what you see here is called the Exploration Medical Condition List. And this is a list of conditions that have either occurred in spaceflight in the past or are believed to have a high enough likelihood and consequence of occurrence that they've been included on this list. Now, there's about 100 things on this list. There's nothing magical about that number of 100. It just turned out that this was the list that was generated a number of years ago. And so we at NASA use this list when trying to define what types of capabilities we need to include in a medical system. This allows us to bound the problem. So we have those 100 conditions, and we can try to scope a medical system to deal with those 100 conditions. Even that system might be too large for an exploration vehicle. But one thing we can't do is how do we then also plan for conditions that we did not expect to occur? A great example of that is if you went back 5 to 10 years ago and you asked anyone if it was possible to drown in space, they would have said that that was ridiculous. And then an ESA astronaut had water in his helmet and had a near drowning event in space. And so that is the type of condition that would simply have not have been planned for if it had not now occurred in spaceflight. So ultimately, the medical risk is not only the things that we know or believe could occur in flight, but we also have to consider the possibility that there are conditions for which we cannot plan that will occur. And the accumulation of those two things is the medical risk. Now, if the medical risk was the only thing that mattered, if my job was to lower the medical risk as much as possible, then the way that I would do that is by simply asking for more and more stuff and more highly trained people to send into space. In fact, if the goal was to reduce the medical risk, then maybe you would send nothing but doctors, and you would just outfit the vehicle with tons and tons of equipment and resources. But the reality is that there's a mission that's being undertaken. And as a result, we have to balance the medical risk with the total mission risk. And we can't ask for more than we actually need. So part of our job is also to find that balance between how much I can reduce the total mission risk by reducing the medical risk without taking away from other systems. So if you give all the mass to medical so we can plan for medical events and you have no radiation shielding, you haven't actually done the crew any favors. So we have to find our balance in the system as a whole. So in order to change the paradigm of the way that we're providing medical care, the way that exploration medical capability is approaching this is we're doing work to better define the concept of operations for medical and human performance. We're trying to better quantify the risks that the human system poses on the mission so that we can explain to vehicle designers and mission planners, when we say we need a thing to manage a medical condition, we can actually put numbers behind why we need it. And ultimately, the decision whether or not to include that technology or that capability is not ours. At least the people making the decision will be able to make the best risk-informed decision. We're also working on data systems for medical devices and technologies and capabilities, and then trying to integrate the human system into the vehicle and the mission in terms of planning. And so I'll tell you a little bit more about these. First of all, I just wanted to draw your attention to this publication that was a number of years ago now, in 2001, that said that NASA had to change the way we're doing business, and we had to integrate the human system into the space mission in the same way we do with every other system. And I'll tell you a little bit more about why we're doing that and how that's working. So this human system is part of a crew health and performance system. And a crew health and performance system for the future is going to have to be able to work more autonomously. Not only is the crew going to have to be self-reliant, but they're going to have to be able to have everything they need on board when they leave, and they're needing to have access to training and support on board in case they cannot reach the ground or the ground delays are too long. And so the integration of all of these components of a medical and a performance system together will allow us to build ourselves into the vehicle and into the mission and enable the crew to function more autonomously. We then have to recognize that we will interface, both the human system and the health and performance system will interface with lots of other systems on the vehicle. And so again, if we develop a system that requires a huge amount of power, and that system then takes power away from other critical vehicle systems, again, we're not really helping the crew out very much. So finding that balance, integrating with all the other players is very important. And so the way that we do that is, as the system is being designed and engineered, there has to be a space at the table for the human system and for the health and performance system, so that as the vehicle is being designed and as the missions are being planned, people think about the impact that the mission will have on the human. And as they make changes to their various other systems, there's always someone at the table who will understand how the human is affected by those changes. And it's the interaction of all of these systems that enables a successful mission. Here are some examples of the types of functions that a crew health and performance system needs to have. And right now, many of these functions do occur in mission on the space station, but they're very independent. They aren't necessarily linked together. And as a result, if the crew is having a problem, People are going to go and look at individual piece parts of various systems to try and identify the source of the problem, as opposed to looking at it as a system and as a whole. And so what we're trying to do is encourage a more holistic approach to crew health and performance. And by integrating all of this, all these technologies and capabilities together, we can not only enable the crew to do their job better and to take care of themselves in mission, but ideally we can also reduce our footprint in general. So if you need a display for 3 different technologies, but you could have one display that works with all 3 technologies, that is a logical solution that we should be taking into account. And right now, the way that we have designed medical systems in the past is in piece parts and not as an integrated whole. And the way that you visualize this as a total system is all of these components together. You also see the crew as part of the system. And then you see our system, the crew health and performance system, as an analogous system to every other one on the vehicle. And so, at least in my previous work, some of the experiences that I have had is that people want to go off and design great rockets and great capsules, and they don't necessarily think of the way that everything integrates together. And the systems engineering approach is one that Exploration Medical Capability has adopted, because we believe that that system approach is going to enable you to ensure that the mission is successful, while also minimizing, again, the footprint of the total size of the system. So then the other question we get all the time is, well, can't we just replace the doctor? Can't we just use artificial intelligence and machine learning and all these advanced computing tools, and we'll just replace the need for the people to take care of each other, and we can automate everything? And it's a very interesting science fiction idea that I would love to see come to fruition in the future. But we, right now, realistically, are still in the crawl phase of that. Even in the hospital on a daily basis, we do not use integrated prediction tools or artificial intelligence. We typically don't have tools that can do image or data analysis that in any significant way, or differential diagnosis generation. So right now, everything is in the beginning stages of advanced computing technologies. And while those may help us in the future, they're still a long way from being real and applied in healthcare on the ground. And so as a result, while we're watching those for space flight, they aren't necessarily going to change anything for us in the short term. Our group does work with a number of different companies and technology providers to try and develop miniaturized and more capable medical technologies for spaceflight. So we work with different ultrasound technologies to try and use them for both diagnostic and treatment purposes. We try to find new technology that will allow us to better monitor the crew and their health state, and then also monitor their performance state as well. You see there that animation moving on the lower right, that's a kidney stone being pushed around inside a person who's having pain from kidney stones. And so that kidney stones are one of the conditions that can occur in spaceflight. And so we are doing some research in that area right now. We're also looking at how to develop a medical data architecture. And this, sometimes people don't think of this as an integral part of how we provide medical care in space. But right now on the ground, we have electronic medical records. We have various different types of technology that does testing and diagnostics and monitoring for patients. And all of that information is captured in an electronic medical record. There's nothing like that in space. The electronic medical records of the astronauts are on the ground. And every time they take a blood pressure, they report it to the ground and someone inputs it into a system. And so as a result of that, knowing what we know about exploration missions, that paradigm simply will not work. And so we want to build a medical data architecture for exploration that allows different technologies to be integrated together and seamlessly, such that the crew doesn't have to be transferring information from one device to another device. We want to minimize the amount of work they have to do, reduce any errors that may occur as a result, and put everything in one place so that they have quick and easy access to it when they need it to provide care to each other during their missions. We also are working on training tools for the crew. We know that we can't possibly train them for every potential event that may occur in flight. And we also know that even if we do train them for how to provide a particular type of medical care on the ground, that might be a year or so in advance of their mission. And when they actually need it in flight, they may not have very good recall for how to do that procedure. So as a result, we're working on just-in-time training tools that the crew will be able to use in flight as refresher training, as just-in-time training for when they need to do a procedure. And then ultimately, we hope that they'll be able to use the same type of tools to autonomously perform these procedures. Because right now, if they want to take an ultrasound of someone's kidney in flight, they need a lot of guidance from the ground. And an autonomous crew of the future is going to need to be able to do that type of medical task on their own. So lastly, here you can see some work that we're doing to try and enable this autonomous capability. And so here, someone is using augmented reality to perform an ultrasound. And as they're performing the ultrasound, they're getting real-time guidance from the system about how well they're doing the procedure, and then also providing them with suggestions and corrections for how to do the procedure better. And so these are the types of technologies that we're looking at right now that will enable autonomous medical care for exploration missions. Our hope is to do all of this work progressively over time and then start to incorporate these technologies and these operational paradigms into our missions as we go forward. So we don't want to do all of this work just for Mars. We need to verify and validate that the work is helpful and is achieving what we want it to achieve in subsequent missions over time, so that once we get to a Mars system, we can have confidence that it's going to work the way that we want it to. And so our interest in exploration medical capability is to enable some of these technologies on the space station as it is today, on the Gateway vehicle moving forward, and then eventually during our deep space transport and other precursor missions before we actually send people to Mars. So that when we do send people to Mars, we will know that they have a robust medical system that's scoped for the types of conditions that we believe will occur, that fits in the vehicle and helps to minimize not only medical risk, but total mission risk, and allows the crew to autonomously take care of each other. That's our ultimate goal. And so with that, I'll just draw your attention to a few of the conclusions. We have to look at medical risk in the context of total mission risk. And historically, that medical risk or human system risk has been undervalued by the vehicles and the missions of the past. We believe that the best way to mitigate the risk is to fully integrate the human system into the vehicle and the mission design. And it's our intention as much as possible to use gateway missions to develop a rational stepwise approach to changing the paradigm of how we provide medical care in spaceflight. And with that, I will end and cede the floor to Anthony.
Thank you, Chris. This is Jules here. This is a great overview of the current thinking in this domain. I love that you have shown a light on what you are doing with the element within NASA on this topic, and shared with us some of the analytical thinking or engineering thinking behind the planning of future missions. I'm sure there'll be questions still for you, and I've seen some of them in the chat box already. We will get to that later in the session. This is the moment that I'd like to introduce our second panelist, Anthony Yuan. He's with us from New York City, and he has been involved in space projects, and as I said, is working as an emergency doctor in terrestrial healthcare at the same time. But I'm sure he will share with us this himself. Over to you, Anthony.
Thank you so much, Juice. Now let me just share my screen. Great. Thank you so much, Chris. I think I listened to you talk quite a few times, and every time I learn something new from your talk. For my presentation, I want to give you a perspective from a terrestrial physician, a bit one that's very much interested in space medicine, about how do we take some of the stuff that Chris has discussed here today, and what is its relevance to us on the ground and for the space industry as a whole. So hopefully I'll go through, where's the applications and why is it relevant to us. So I always kind of put up this slide because when we talk about space medicine, yes, it's very much people will think about providing medical care for astronauts, but there's two paradigms here. It's about humans in space. It's also about how space for humans. And I love to always put aside so that keep us thinking about both of them, because even though when we're talking about exploration medicine, both of these things still need to be thought about, because anything that you do for exploration medicine, it will still be applicable somehow on Earth. And I hope to show you this. So what Chris kind of have talked about is really how do we provide medical care and emergency medical care in the context of exploration missions to the moon, to the Mars, and beyond. Now, this kind of framework and investigation and exploration is very much the cutting edge of space medicine. This is really where, we're talking about the space agency pushing the real boundaries of our understanding and the limits of our human existence past the moon and beyond. And so when we kind of working on these cutting edge ideas, there's kind of opportunity to think about how some of those things can be applicable in other settings. And one that I really like to draw your attention to is, what is becoming known as the cislunar or the LEO economy. This year has been very exciting in that Virgin Galactica performed pretty much the first commercial space flight or suborbital tourism flight testing in preparation for taking its first paying passengers soon. And that's really exciting. I think that's really kind of the milestone where we hit, where we're starting to really see space being opened up, not only as a place for exploration and science, but also for other aspects of the economy. And I have here on your screen on the left here, kind of, Tony Bruno love putting this picture up, but I guess that's actually where we're heading, is basically developing the infrastructure for people to be working in space, because space is actually going to be offering something for Earth's economy. And this is quite different to exploration missions, in the point that it's not really kind of focused purely just about preparing for a mission, but you're going to have people in space who might be doing their job, who we now have to be prepared for whatever medical care that they're going to come up with. So it's pretty much taking out the same idea in exploration missions in terms of what kind of medical equipment do you bring, what kind of condition do you prepare for, how do we treat certain conditions, what needs to be evacuated, because luckily in LEO we can evacuate. and basically applying to a much broader and bigger population and perhaps a less healthier one. And so that's really kind of very similar, but at the same time different approach to exploration missions. And we learn a lot from the experiences from exploration missions to be able to apply to medical care around the LEO and cislunar economy. The other relevance to us on terrestrial ground is with all of these companies, SpaceX, Virgin Galactic, and Blue Origin, sending people up and down to space, basically, you're now looking at people who are maybe no longer really training a lot for these missions, who may already have pre-existing health conditions, because, come on, you know, a lot of people have to work till 40, 50 before they earn enough on all these tickets. And now they're going on these space flights where it could actually be, you know, some sort of stress on the body. So how do you prepare for that? And so really we're moving from focusing on these very healthy people going to space to where basically space is going to be another extreme environment where patients is going to be coming from. Very much like people who climb the Himalayas, the mountaineers, people who scuba dive. How do you prepare for issues that occur in those settings? How do you provide care while they're in those environment? And how do you provide care after they leave that environment? All of that really is changing up the idea of how emergency medicine, as well as other aspects of medicine, is being done on the ground. And so even for your normal terrestrial physician, you know, there's going to be a greater need to understand how do you treat patients who has been into space, because there's just going to be more and more of them. And so that's also a changing paradigm on the ground for any physicians, is that space really will just be a more common extreme environment. Now, moving on is, you know, we always talk about developing technologies and methods for exploration medicine. But the greatest part of that is that there's always an application to Earth. And even in, you know, NASA's work in developing these technologies specifically for exploration missions, there's always a need to talk about how that can benefit back on Earth, because it is, at the end of the day, you know, taxpayers who fund these missions. And there is a lot of tremendous potential for these technologies that was developed for these missions for widespread use on the ground. And NASA often cites, you know, for every dollar that the government put into NASA, about $7 comes back into the US economy alone. And so this is important because, you know, this moves space away and exploration missions away from a realm of, hey, this is great science fiction that, you know, people want to do, to a place where, hey, it actually is changing things on Earth. It's making Earth for the better. And it's well worth us, everybody in the world, investing in this, because it provides for applications on Earth. And here, you know, I talk about two kind of key things is, you know, how do you do better medical preparation for exploration, but also low resources environment on Earth, and also for in disaster zone. You know, a lot of the procedures and techniques that can develop in exploration missions have a lot of applicability on Earth. And how do you disseminate that? How do you bring that technology back on Earth, make it low cost, make it available everywhere? And same very much with telemedicine. You know, right now, telemedicine is right at the cusp. It is being well taken throughout the world, but there's certain technical issues on the ground to make that possible. How do you get good enough bandwidth for communication to get high fidelity video so that you can actually visualize the patients properly? Can you get additional bandwidth to carry additional signals, such as the patient's vital signs in real time? But even to the point where can you actually get good enough signals where you can guide somebody using an ultrasound probe across the other side of the world, how to take better pictures so that you can make a diagnosis from where you are. And so those things are pretty much very much applications of exactly what Chris has talked about on Earth that can be applicable anywhere around the world. And that's where a lot of the potential, and that's where a lot of the work is in this area of space medicine. And so I think, one question I get a lot as the lead for space medicine and life sciences project group is, what can you get involved? Obviously, the agencies, the space agencies, the space companies need, physicians and engineers to develop these medical equipment. But a lot of the bigger picture thing is about developing solutions on Earth that can actually be applicable to both space and Earth. And this is where the realm of potential startup companies, where you're developing things that has very much space application, but also has a market for Earth. And this is very much the trend that I've been seeing when I go to conferences where they have a entrepreneur pitch session, is that a lot of the successful pitches, a lot of the successful companies, quite a few of them are actually medically related. And very much they are very focused on key issues in exploration medicine, exploration space medicine. But at the same time, they are able to kind of figure out how that application can be applied on Earth, and how that economy of scale and how that product and service, which creates an economy and creates revenue, can fund further research to make the space part, the application to space, even better and even more cutting edge. So some of these kind of key areas that I often see, that I like you to kind of think about, and because everybody's expertise is very different or have a very different interest, but these are the things that are really hot right now. Definitely, Chris talked about machine learning, artificial intelligence. We are very much in its infancy, but there's a lot of potential, especially in medicine. And medicine is probably one of the slowest industry to take up AI. We're about probably 10, 15 years behind in compared to other businesses and other industry fields. But there's a lot of interest in it, and as well as there's a lot of interest in investing in this area. And you can see the application in exploration medicine. We can talk a lot about developing medical technology and tools, especially for the low resource settings. So right now, the ultrasound machine has been shrunk from a big thing on a cart to a little tiny attachment to the iPhone. Not as good picture, but it'll work in wherever low resource settings that you are. And so this is an area, with new sensors and so forth, that really is very, very exciting as well. I talked a little bit about the potential for telemedicine and how that really can offer a lot of different changes the way how we do medicine, because we no longer depend on having someone there at the hospital. And then we talked about AR and VR. Here I mentioned mental health and well-being, which is one of the biggest research area right now for AR, VR, but for many other things, for training as well. And finally, about managing medical risk and medical issues in missions, which is basically what Chris has taught. So I hope I kind of expanded your mind a little bit about the from the excitement from Chris's talk about how applicable and how approachable all of these issues in space that you can be involved in solving through doing something like this. So I'll hand this back to Jules.
Thanks, Anthony. Thanks for sharing about how terrestrial healthcare and space healthcare and the medical preparations for human space flight actually benefits from each other, and where some of the current challenges lie. This brings us to the Q&A part of this episode. I turn to the audience now, to you. This is your chance to engage with our speakers. Feel free to unmute yourself and ask your question aloud. We'll try to moderate these. We have a few minutes, so maybe one or two questions. If you are unable to use your microphone at this moment, you can leave the questions in the chat box. Is there anyone who wants to start off, or otherwise I'll hand you something from the chat box? I see here somebody asking, should we expect more mental health issues as deep space missions get longer, including the communication delays? Is there any one of you, Chris or Anthony, who wants to comment on that.
Sure, this is Chris. I think that there's no doubt that support for the crew in terms of their mental health and their overall performance is going to get more challenging, not only with communication delays, but also there's a lot of discussion about what will happen to people when they look out the window and they can no longer see the Earth, and what type of impact that will have on them. There's a lot of work being done at NASA to try and develop training and capabilities that help the crew to improve their resilience, to be more cohesive as a team, to be more self-reliant and perform more self-care, if you will. But a lot of that is reliant upon communications. And so as the communications become more challenging, the mental health issues could certainly increase. And that is a real concern that NASA is working on right now. And we're trying to create standards for our missions and requirements for our missions that enable the crew to stay as mentally healthy as they possibly can, despite the challenges of exploration. But it is an area of ongoing work at NASA. And I encourage anyone that's interested in getting into that area to do that, because there's a lot of applicability, as Anthony mentioned, not only in space, but also on the ground.
Exactly. All right, thanks. If anyone wants to ask their question out loud, just chime in. Otherwise, I'll go ahead and find one more from the chat box. I see here Egbert from the Netherlands, who I know is working on some of the biological challenges of manned spaceflight. He's asking, I was wondering to what extent studies or projects regarding human hibernation are progressing to tackle some of the mentioned challenges.
So this is Chris again. I can say that NASA has looked at the hibernation as an advanced concept for the future, but NASA is not currently working on any technologies that apply that concept. As it stands right now, there are many challenges to the idea of human hibernation for long duration space missions. It's somewhat akin to the engineering challenges associated with artificial gravity. It's not that it's could not be a viable option in the future, but the time between now and then is significant. And there's a lot of work that would need to be done in order to make it applicable to space missions. I would say right now that NASA is doing more research on advanced propulsion techniques so we can get to where we want to go faster, and use that as a better countermeasure against long duration spaceflight.
All right. So a question of my own. We might get there a little bit faster, but still the journey will take some time. Through my work, I got involved in the development of some training programs using virtual reality or augmented or even richer forms of extended reality. Do you see those types of technologies, you mentioned some of them, and the training programs being realized just for ground-based training only, or also for onboard training or keeping current for some of the skills that maybe some medical skills that astronauts would need?
I think that those technologies are very likely to be used on exploration missions, not only for entertainment purposes, but as you mentioned, for training purposes in flight, for guidance during procedures as well. I think there's a number of applications for augmented reality in flight that have a significant amount of potential.
Great to hear. Actually, we are at the top of the hour, which means that we will have to conclude this first episode of the Health in Space series. There's still some questions coming in the chat box. Perhaps you can send them on Twitter for our speakers. I know both of them are online on Twitter. Maybe some of them can answer them there. We have heard a lot today. I learned a lot today. Thanks to our wonderful speakers. I'd like to give many thanks to Chris Leonhardt and Anthony Yuen. Thank you for being with us today and sharing your stories. As for the Health in Space series, this was our first session, but we are evaluating new topics for new episodes. We have a whole list of fascinating topics that come to mind when thinking about health in space. But if you have a topic that you are passionate about and want to learn more about, let us know. You can send us an email through the invite to this webinar, or find us on LinkedIn, Twitter, and we'd like to create this series together with you, our audience. That was it for today. Thank you. Thank you again for panelists, and thank you for everyone that joined us from around the globe. Have a great day ahead and see you next time.